Hello everybody, welcome to this new video where we're going to solve an astronomy problem by the name of final wave. So in this problem, a 7300 Kelvin star, that's the temperature of the star, in a Milky Way-like galaxy 3 megaparsecs away is seen revolving. It's located at the constant part of the rotation curve, moving away from us. So when observed, the ratio between the linear and tangential speeds are 2 to 1. At what wavelength do we see it? And we should also explain all assumptions. Alright, so first we look at the galaxy. To make it simple, I've also drawn a diagram here, so we can visualize it more easily together. So let me explain this diagram. So over here, there's a star. Yeah, the star in there, and this is the center of the galaxy. So you see, like it has been stated that there's a tangential velocity right here, and a linear velocity right there, such that the resultant of these velocities are this velocity, the constant velocity of the star rotating around the center of the galaxy, its rotational velocity. Uh, yeah, it's a constant part of the galactic rotation curve. So why is this galaxy something that we have to look around? What significance does it have? So we know the concept of Hubble's distance, with the Hubble's constant being 70 kilometers per second per megaparsec. Uh, so we know that the velocity is equal to Hubble's constant multiplied by the distance. Remember that the galaxy is very far away, as stated in the problem, 3 megaparsecs away, such that the linear velocity of the galaxy is 210 kilometers per second. Now, this linear velocity is just of the star, so we haven't drawn that on the diagram. Rather, we've only found this one. It's the linear velocity of the galaxy. And for this problem, we're going to assume the galaxy as a solid object, as in it doesn't change shape, even though it seems to be moving away from us. But for an observer inside of the galaxy, it doesn't. So yeah, gravity is quite strong. And next we take into effect of the star. Now, as stated earlier, the star is located in the constant region of the galaxy's rotation curve. You see the rotation curve of the galaxy, velocity to distance, of course, it goes up in the beginning, right? It goes up at some kind of constant rate, and then it stays constant. So basically, we take this as the velocity of the star. Now, the problem also stated that the galaxy is like the Milky Way, so we can assume that this velocity, or the peak, or the constant velocity, which is the same, is 220 kilometers per second. Now, what can we do with this information? We know that the velocity, the linear, which is y, over here, and the tangential, or x, it's 2 to 1, and the resultant of these velocities, the scalar resultant, is 220 kilometers per second, of course, such that you can substitute Vy is equal to 2Vx, and you can put that in the equation inside of the square root. When we do the math, we get that 5Vx squared is 220 squared, or we can say that Vx x is equal to 220 over the square root of 5, and with that Vy is just 2Vx, 440 over the square root of 5. We can simplify. Vx is 44.5 kilometers per second and Vy 88.5 kilometers per second. Alright, so what about the total velocity of the star? Well, before that, we must find here lambda 0, or the wavelength at which the peak wavelength at which light shines in this star. We just have to use Wien's law here, and we get that the wavelength at which the star radiates light, the peak one, is 3.813 times 10 to the negative 7 meters. Then we use the total velocity of the galaxy and the star. Notice we only use the velocity that's moving away from us. Well, why is that? Well, that's because the velocity for the one that's the tangential velocity, it's not that important, as it really kind of stays in the same place for our perspective. It's only 44 times the square root of 5 kilometers per second, whereas it's located 3 megaparsecs away from us. So it really doesn't make much of an effect. So we find the total velocity here. And we see that this velocity is small, relatively small, you can say. It has a redshift of less than 0.1, such that we can just use the normal Doppler right here. Delta lambda per lambda 0 is equal to delta V over C. Find delta lambda is lambda accent minus lambda 0, and delta V over C is this V right here. Alright, we do some more of this math. We take out the lambda 0 from both sides, switch it from the left to the right hand side, and we multiply everything by lambda 0, which we've already found here, such that lambda accent, or the light that we receive on Earth because it has been redshifted, is equal to lambda 0 multiplied by V over C plus 1. And when we plug the numbers in, we will get 3.818 times 10 to the negative 7 meters. Alright, that's all for today's video. I hope you enjoyed and learned something new. Thank you.